All right, there we go. Hi everyone. Today I'm going to be talking about the flight dynamics ground system for the OSAM-1 mission. Now, before we get started, I should briefly introduce myself. My name is JP Burke, and I've been with AI Solutions since the summer of 2016. I come from more of a software engineering background than an aerospace engineering background, so I tend to look at system design a little bit differently. I started out working on the EOS missions, Aqua, Aura, and Terra. I helped out to automate some aspects of their ground system. And in July of 2018, I moved over to the Restore L ground system back before it was renamed to OSAM-1. And I'm currently the FDS ground system lead for OSAM-1. What you're going to see today is I'm going to walk you through the OSAM-1 concept of operations, what the mission's all about, some of the flight dynamics challenges of OSAM-1 and the kind of day-to-day what it'll be like for the FDS operator. We'll do a live demo of maneuver targeting and product generation in our system, and we'll do a walkthrough of the software architecture and data flow all the way from the user down to products and back again. So before we get into the details on the flight dynamics ground system, I wanted to briefly go over the overall concept of operations for OSAM-1. OSAM-1 stands for on-orbit servicing and manufacturing, and that really kind of sums it up. For the servicing part of that acronym, we're going to be rendezvousing with the Earth observation satellite Landsat 7. Landsat 7's been up there since 1999, so it's really low on propellant. It's basically just running on fumes at this point. We're going to capture it, we're going to refuel it, and we're going to send it on its way. It's pretty tricky to do since Landsat 7 was not designed to be rendezvoused with or serviced. This video is right now showing the capture right at the end of autonomous rendezvous and docking. It's going to grab it by that ring there where it was mounted onto the launch vehicle, which is kind of the only safe place to grab it. Moves it down onto these 3 berthing posts, and then the rest of this video really focuses on the servicing phase, which is when the robotics team gets to show off all the cool stuff they've been working on. You know, it's going to use a saw to cut open some insulation. It's going to cut some of these wires that are preventing the caps from being accessed. It's going to take these caps off of the fill and drain valve, and then it's actually going to transfer some propellant and allow Landsat 7 to continue doing what it's been doing. So it's pretty cool. It's got a whole bunch of different tools up here and all these different robotic arms to account for any issues that might come up. And there's the propellant transfer hose, and I'll give it a second here to show their little indicator of propellant going in. Oh, they're also going to leave a nice quick disconnect valve here, so if they ever want to service it again, it'd be a lot easier than this time. For the assembly and manufacturing part of OSAM, we have another payload that's going to be doing a few different things. This video is made by Maxar, who is our spacecraft manufacturer. I just took this from their YouTube page, so thanks to Maxar. For assembly, the Spider payload, which you just saw there with that robotic arm, is going to take a bunch of antenna parts and actually assemble them into an antenna, and then they're going to characterize the beam that comes off of that antenna. And then the MakerSat payload here is going to extrude a beam while in space, and then it's also possible to remove it and stick it back on, which is kind of this interesting modular spacecraft design. All this is kind of in service of a future where they could start building more complex space missions on orbit with robotics. But none of that really has to do with what I'll be talking about today, which is the flight dynamics. These are some plots that I got from the folks on the analysis team, and I've really just included them because they're a good visual indicator of how complex the flight dynamics are on this mission. They're not even really from the part of the mission I'll be talking about today, but I didn't have plots for that, so I included them because they're pretty nifty and they kind of showed that general sense of there's a lot going on for this flight. In order to make this mission more approachable, it was broken down into a number of phases, with each phase being sort of a smaller mission on its own. The phases are transit, autonomous rendezvous and docking, servicing, departure, assembly and manufacturing payload, and finally deorbit, where we dunk it in the ocean. Today I'm going to be focusing on our systems for handling transit, since they're the most mature, and it'll allow me to do an actual demo of our system a little bit later. Transit is the phase where we clean up the launch dispersions, we check out all of our sensors, and we deliver the spacecraft to a specific target point relative to Landsat 7, which is 100 kilometers behind and 5 kilometers below the spacecraft. In the current ConOps, the transit phase includes as many as 12 targeted maneuvers, and depending on how accurately the launch vehicle drops us off. If they're perfect, then some of those maneuvers won't be necessary. Within a few days of orbital insertion, we do the first of 2 potential inclination cleanup maneuvers. then a few days later, we have a co-elliptic burn pair designed to clean up any dispersions in our semi-major axis. And then we coast for a while as we phase with Landsat 7. And then after that, we perform what's called the mini rendezvous, which is sort of emulating the tasks of the next phase, the autonomous rendezvous and docking phase. And that's going to make sure that that phase will go smoothly. There won't be any surprises. Lastly, we have 4 co-elliptic burn pairs spaced out over about a week, which control phasing and deliver us to our goal point, which is called Authority to Proceed 1, or ATP1. Almost all of these maneuvers need to be retargeted regularly based on updated orbit determination for our spacecraft, orbit determination for Landsat 7, and desired conditions during capture. So during the early part of the mission, a day in the life of an FDS operator is going to include getting the fresh orbit determination data, ingesting that into the maneuver planner, retargeting all maneuvers left in the sequence, and then generating fresh products based on the new predictive ephemeris that resulted from those updated maneuvers. These products include some pretty basic stuff like eclipse times or TDRS view periods for scheduling communications. They also include some mission-specific products, such as when we'll be entering or exiting our desired capture region. That was a whole lot of talking, so I'm going to get into a quick demo of how we expect operations to go. So I'll switch over to this. What you're going to be looking at here is a very early version of our main FDS user interface. It's missing a whole lot of functionality that we plan on having a little bit down the road, but it's real and it's working. So I thought it was worth showing. But I just want to emphasize, like, don't worry, we'll be adding a lot more useful stuff and polishing the appearance. This is going to take about 90 seconds to run, so I'm just going to start it and explain what's happening while it goes. When we retarget maneuvers in the transit phase, we're going to take a slightly different approach depending on what the anchor maneuver is, which is what we call the next maneuver in the sequence. So if the spacecraft is on orbit in between Ascent 2 burn pair and the Ascent 3 burn pair, then the anchor maneuver would be Ascent 3 since it's next. But we still need to retarget all of the maneuvers along the way to make sure that we can still get to ATP1. So here I've chosen Ascent 3 as my anchor maneuver since it's going to run relatively quickly and allow us to do this demo live. We haven't implemented loading of fresh orbit determination data into this yet, but so you can kind of imagine that what will be closer to operations would be we would choose on this interface to select an EFEM that's the latest definitive ephemeris to give a state vector from the end of that, so we know where the spacecraft is and where the targeting has to take place from. Down here, you're seeing a whole bunch of text output. That is actually the live console output coming from FreeFlyer. We've got, this is using our logging procedures we wrote that use kind of traditional logging levels, and we put some nice colors to make stuff stand out that needs to stand out. All this blue text is just debug level, and we don't need to necessarily pay too close attention to it unless something goes wrong. Info level is just letting us know kind of where we are in the overall process. So this should take a few more seconds here, and then it'll start generating an EFEM. And what's great about this setup is as it's generating the EFEM, it's also going to pop up an unconstrained FreeFlyer window, which should be coming up in just a little bit here. I don't see any issues with this, so I think it'd be wrapping up. The ability to pop up this like an interactive, there we go. So there's a little bit of warnings. These are expected warnings. And here's our window. So this is our live plot of our SMA. This is the purple line here is our SMA compared to the target SMA, Landsat 7. This is a fully interactive plot straight out of FreeFlyer. I can zoom in and take a look at this stuff to see, here's where the maneuver happened, and it's pretty cool that despite not having the full FreeFlyer interface open, I can still pop up these individual windows and get some use out of that. But all that was just generating this predictive EFEM down here that's, contains our new targeted maneuvers. It also output what those maneuvers look like, so I can kind of, we can do a spot check on the logs or run it through something else to check. But for now, we're gonna go ahead and run it through our orbit products generator to actually make some products. So I'm gonna go ahead and choose my EFEM here, choose the attitude history file. And one thing I want to point out with this is that we have a lot of control over the configuration of how this is run. Right now, I have a default configuration loaded that I can override a couple of the values included here, but it gives us a lot of control. So without having to change any of the code. So for instance, let's say for whatever reason we want to change the default Chebyshev fit span from, I believe it's 48 hours to 50 hours. We could just put that in and it would pass that along, and without changing any of the code, it would go ahead and update that. So I'm going to choose a couple of products here that look interesting. We'll do this, and I guess since we don't want it to take too long, we'll tell it to only run for half a day. And I'll go ahead and hit that. This is just kind of an overview of some of the products we have available now, a little bit more. I think as we keep going, we're also going to have a lot more configuration here. The plan is to kind of, have defaults that we can rely on, but then have the flexibility to be able to override these values if necessary during ops. So again, this thing is loading all of our sensors onto the spacecraft. Right now, it's loading all of the ephemerides for TDRS. This will take about 30 seconds or so. A couple of expected warnings based on how I generated that EFEM. It's already done making the eclipse periods. In fact, it's already done with everything. So it's output that it finished line of sight, it finished Chebyshev's. Total time took 34 seconds. And in fact, we can now go to the file system, go to our products directory, and then here's real deal products made right before your eyes. So here's the Chebyshev coefficients. We use this to tell the spacecraft where TDRS satellites are going to be, so we don't have to uplink an entire EFEM for that. So this way it knows how to pass the, how to point the high gain antenna. So all of that was basically what we're doing, but now let's talk about how we're going to do it, or how we are doing it. We had a few goals for this ground system before we even got started writing any code. First and foremost, we wanted to leverage the team's skills in FreeFlyer. Most of the team was already extremely adept at using FreeFlyer, so we wanted to make sure that all the heavy lifting was done there. Next, we wanted to create readable, decoupled, and maintainable code. Again, I come from a software engineering background, so I had a number of best practices in mind that I really wanted to try applying in an aerospace project. Most of our time interacting with code is actually spent reading it. Whether it's reviewing a teammate's code, familiarizing yourself with a function you need to use, fixing a bug, or looking for the best way to add a new feature. So readability was really important to us, and we wrote a pretty strong coding standard and some practices that have, I think, really helped us out. We also wanted to prevent changes from propagating through the system too much. So if we had to change one part of the system, we didn't want to have to then run around changing it all over the place. So we really strove to make a nicely decoupled code. And we, lastly, since we're going to be living with this code for a while, we wanted to make sure that it was as maintainable as possible. We also want to have a rich user interface that allow us to have a lot of flexibility and rapid iteration. That's because nobody's ever done a mission quite like this before, and we expect that as development progresses, we're going to have different ideas about the best way to interact with our systems, and maybe our initial ideas weren't quite right. So we wanted to make sure we had the ability to respond to those as they come up without a whole big headache. We wanted to changes in operations to never require changing code. You saw this a bit with my example of the Chebyshev polynomials in that live demo. In a perfect world, we'll never touch a single line of code during operations. We want to write it early, test it, get confidence in it, and then run the mission with that, and any small tweaks can be handled in the configuration. And lastly, we wanted to make sure that all these other goals didn't set us up for an incredibly difficult development phase. We wanted to keep things nice and decoupled so people could work on one part at a time without having to get into the entire end-to-end, get that whole thing working first. All right, so this is an overview of the architecture for the code running the demo that you just saw earlier. There's a lot going on here, so I put these little numbers in circles to make it easier to take this step by step. First, we're going to start with the FDS operator interacting with the main ground system UI. That UI is actually a lightweight web page, since that allowed us to make really flexible interfaces without a ton of extra complexity. The user makes their selections on the page. I should point out that this page is hosted locally on the machine itself. There's no central server. It's not going over the internet or anything. This is just all on the same machine. The user makes their selections, they hit submit, and the request is sent back to our main controller via an XML HTTP request. This allows us to send the request in the background without leaving the page. Our main controller is written in Python, which was chosen for a couple of reasons. First, Python is commonly used in science and engineering applications already, so it was more likely that to find people who were already comfortable with it. Second, for those on the team who are unfamiliar with Python, it would be worth the trouble for them since they would be able to continue to use it on other tasks later on. And third, it had a nice library called Flask, which allows for clean organization and separation of all the different actions that might be requested by the front-end UI. Oh, let's not scroll ahead. The role of the Python controller, in short, is to prepare the input for FreeFlyer and then relay the results. It does this by receiving the request from the user. It checks certain files in the file system. It'll retrieve configuration information from a database. And once it has everything ready to go, it builds an object, which is essentially just a key value pair. And it converts that into a JSON string. If you're unfamiliar, JSON stands for JavaScript Object Notation, and doesn't necessarily have to be used in JavaScript. It's just a nice standardized way to bundle a bunch of complex data into a string, which is then easily portable to anything else that supports JSON. I'll go back to the data flow slide in a second, but I just want to show a quick example of this JSON config. So this is a portion of one of our configuration, our JSON configuration files, just kind of showing what you would expect of, key, don't click things, being like the capture region file path, and then here's the path, what do we consider to be the maximum minimum shadow, and this is what gives us that extra flexibility over how the code is behaving. Once we have our JSON string ready, at that point we're down here in just underneath step 2, the Python controller will then spin up an instance of FreeFlyer via the FreeFlyer Python API. This is a super convenient feature where I can interact with FreeFlyer automatically using commands in Python. Down here, you can see how we have a bunch of different FreeFlyer mission plans. As part of our goal to keep things modular and decoupled, we really tried to keep each mission plan focusing on one thing and one thing only. And when you do that, you end up with a larger number of smaller mission plans. So the Python controller's job is to know which one to call. So it looks at what the request from the user was, and it knows what mission plan to load up. It loads up the mission plan, and once that's loaded, it injects the configuration into it via JSON. It basically, literally just sets a string inside the mission plan that expects to have JSON input in it, and it will just set that string with the configuration. FreeFlyer then loads that using the JSON parser, loads it into its configuration, and just chugs along at whatever its task is. If it's the maneuver planner, it's going to be writing EFEMs and maneuver data and reports to the file system. If it's the over products generator, it's going to be writing all those products. And then we have a whole bunch of other things I didn't include. When it's done, it lets the Python controller know how it came out, whether there are any errors or whatever, where it stored those files and what the general outcome was. While FreeFlyer is running, the Python controller will periodically poll FreeFlyer to get fresh console output, and it sends those to the front end so the user can monitor the progress. That's the log lines of the blue and the white and the yellow that you saw earlier. The JSON injection method may seem like it's a little bit overly complicated at first, but there's a reason for it. We knew it was going to take considerable effort to build out the user interface, the Python controller, and the database. But since the beating heart of the system is the FreeFlyer mission plans, we wanted to make sure that development on that could start right away. So when these mission plans start, the first thing they do is they check to see if they've received that JSON configuration string via the Python API. And if they haven't, then they say, oh, well, I must be running in standalone mode, and they look for a JSON file on the file system, which is depicted here. So we can kind of chop off the top of that entire structure we saw earlier, and it just reads in all that configuration from a file right next to it, and continues on its way from there. If it doesn't find the file and it doesn't find the string from the API, it says, what are you doing? And errors out and stops, but it can only do so much. The important thing to notice here is that FreeFlyer doesn't know or care where, like the rest of this mission plan doesn't know or care where this configuration came from. Only the very top of the mission plan, which deals with getting it from the API or the file, ever has to think about this. For the rest of the mission plan, it's the configuration. It doesn't know, it doesn't care. So that means that we can start working on the mission plans without having the full system in place yet. And if you have someone on the team who specializes in FreeFlyer and maybe not Python or the database stuff, they can easily develop on their own with this, and then later on, you can integrate it into the overall system. What's really interesting about this is we actually started development on this ground system around a year ago, but only started on the user interface, really only a matter of weeks ago. And just we were able to do that, since we had the confidence that, with this configuration coming in through that JSON string or file, once the time came to add in the stuff and hook it into the greater system, it would just work seamlessly, and that's exactly what happened. So it was pretty satisfying to see that in action. What's also super handy about having the standalone mode is when we're running it through the API, we can watch what's happening and we can issue commands. We don't have quite the same level of insight as to what's happening as when you're running FreeFlyer itself. With the standalone mode, like let's say you're running an API mode and there's some issue that, it can't target. Okay, you can open it up in standalone mode without a lot of fuss, and now you've got all the power the FreeFlyer has to offer. You got the full development environment. You can, see the types of all your variables. You can open up the help to double check that you're calling stuff right. You can, and probably most importantly, you can use the debugger, so you can step through stuff line by line and, pause execution in mid-flow to see what the state of everything is. So, we kind of got the best of both worlds there. We got this really nice streamlined approach that makes it so you can't, change anything by accident in our main UI, but we've got all the power available to us, within seconds if we want to switch back to standalone mode. And I think this flexibility to run in either mode like this has been a really big asset to our team. It's allowed us to really focus on the heart of the system, the most important part, and treat the UI integration like a solved problem. And once we finally went to hook it up, it just worked. So to kind of wrap up here, we chose FreeFlyer for the transit phase to retarget dozens of maneuvers per day, and it also is going to be doing hard work on all the other phases, which, believe it or not, the transit phase is, perhaps not the most complicated area. The AR&D is going to, autonomous rendezvous and docking is going to be a whole other interesting challenge. FreeFlyer's API allowed for integration into other technologies, increasing the flexibility. So, we were able to easily hook this up into Python, which also then allowed us to hook up to our database, to our front end, or anything else that we might need down the road. JSON support really facilitated interoperability with other technologies. Oh, there's the cat tax for you. So just the fact that JSON is this really nice portable format supported by a whole bunch of different things. It's human readable, which is really useful. So, if there's an issue with, why did it use this path instead of another one, you could just load it up into a text editor and see it, for yourself. And so far, it seems like the goal of not changing code during ops is achievable. Even just using the system for setting up this demo, I found myself using just changing stuff on the fly to meet my needs without having to go and either change stuff in a database or change things on this on the file system. Definitely not have to change things in the code. So it was, it's really kind of unlocked, again, kind of the best of both worlds here. That is the end of my slides here. So I'm very happy to take any questions anyone has or go back to any slide that anyone wants to take a closer look at. So thanks.
Great. Thanks so much, JP. It's really interesting learning about how FreeFlyer is used in a real or a future real flight dynamic system, especially one that's as complicated as the OSAM-1 mission. We do have a question. The first one is, so you talked about needing to retarget based on an updated OD for OSAM-1 and Landsat 7. Are you evaluating or monitoring CA or conjunction assessment with other objects during the ATP phase when the two spacecraft are connected? And if so, what are you doing to mitigate a high-risk close approach?
Yeah, so I don't know all the ins and outs of the conjunction assessment ConOps, but I can tell you that we're going to be working closely with Kara, and we'll be generating a whole bunch of EFEMs to send to them, including stuff like for instance, during AR&D, there's a whole lot of maneuvers in a relatively short amount of time. It's only like a 40-hour period. And so, for instance, we'll be generating an EFEM based on if everything goes right, but also if any one of those maneuvers fails, we will calculate a no burn from that point on. And so we'll be able to submit all those EFEMs over to Kara to make sure, like, at any point are we looking at any trouble. I'm not sure. I think for stacked operations, I believe one of the first things they do is they do kind of an engineering test burn to make sure they understand the characteristics of the stacked structure so that if the need comes to do a risk mitigation maneuver, they're ready to go on that. But yeah, we've got we'll be keeping a close eye on that throughout the mission.
Yeah, and just for external users, can you mention what Kara is, what they do?
Sorry. Yeah, CARA is it's a group at Goddard Space Flight Center who do conjunction assessment. I forget what it stands for, but it's CARA, CARA. I'm betting the CA stands for conjunction assessment.
It sounds like a sure bet.
Yeah.
Thanks. So next, you mentioned that you're going to be receiving a number of OD states. How many do you anticipate receiving, I guess, per day? And then how would that translate into how you're automating it so that you don't have an operator constantly having to, ingest new OD states and regenerate new ephemeris files?
Right. That's a good question. I think a lot of the stuff with that, the kind of day-to-day ConOps is definitely in flux. I think we anticipated actually probably not fully automating this and probably just having an FDS operator do this on the order of probably once a day during much of the mission. Maybe as we get into AR&D, when things are moving a lot faster, that's when we might look at trying to either, automate on on an automatic schedule or just, you're right to want to avoid having the human in the loop at this kind of high pressure moments. I'm not sure how often we're going to be getting fresh OD or how many different, what the exact flow is going to be on that yet. But for now, we are anticipating, basically, we think of it as kind of guided automation. We want to have, as the computer, be able to do as much of the, especially time sensitive stuff as possible, but we want a human in the loop to kind of guide it and make sure that that's working. So for instance, you saw me selecting an EFEM for Orbit Products Generator. What we anticipate is that, since like the most likely situation is that you're going to want to use the latest EFEM that you just generated, the application will be able to kind of preload that as a suggestion of like, hey, did you want to do this? And that way, if everything's good, all the human has to do is kind of do a quick look and hit go. But if something different comes up, they have that flexibility to override it and choose different options.
Okay. And so, I mean, you mentioned having the operator in the loop. And I know you had, your log outputs from FreeFlyer. Are you guys ensuring some way for tracking, the responsibility of an operator, like what they're doing, maybe permission-based logging in to your web-based UI to see like exactly what was run with what parameters? I know you have the input and output files that get written, but what are you doing to make sure that everyone knows exactly what everyone else is doing?
Right. That's a really great question and something that we've been kind of thinking about a little bit, but we haven't firmed anything up. I should mention that OSAM-1 is currently targeted to launch in like late 2024. So, we have a little bit of time to figure this kind of stuff out. But yeah, what's nice about another benefit of that user interface is we can track stuff like, have a user log in and be like, okay, well, this person ran the maneuver planner and they overrode this configuration option like this. And, we're going to make sure that, not only are we outputting all those logs somewhere, but like we're going to keep it with the products that were generated and have the ability to kind of reconstruct stuff after the fact based on the actual, real inputs, not necessarily just what the default or expected were. And you're right that we're going to want to, track what each user is able to do. I'm not sure if our team's going to be big enough that we're going to need to restrict certain actions, but that would certainly be something that's doable.
Cool, thanks. And the next, sorry. So the mission plans you've developed in FreeFlyer for OSAM-1, are they specific to OSAM-1 or specifically for robotic servicing, or could those mission plans be generated for a different mission, maybe just a typical LEO mission?
Yeah, so it's interesting. Like one of the reasons that we, did end up writing most of those specifically for OSAM-1, just because looking at the ConOps, there was just so much going on that was different from a typical mission that we thought it was important to, give ourselves that flexibility. We do try to keep things a little bit generic. Like for instance, in our code, most of the time you won't see Landsat 7, you'll see target spacecraft, just in case who knows what. We try to keep things just as general as you can, but like we don't want to create a headache for no reason. We're at the end of the day, we're writing this code for OSAM-1, and if something else if we're able to recycle it later, that'd be great, but it's not the priority.
So just if I wanted to learn more about the history of NASA's human spaceflight missions, while I was driving or something like that, what would be the best way to do that?
All right, I'll keep this short. I do make a NASA human spaceflight history podcast called The Space Above Us. You can Google it, it's on everything. Go to thespaceabove.us. learn all about NASA human spaceflight.
Awesome. Thanks so much, JP.
Thank you.